Nearly 50 years into an extraordinary era of space exploration, NASA's Voyager probe has encountered a critical malfunction that put its deep space mission at risk. In response, NASA assembled a team of expert scientists and engineers to execute a complex systems upgrade and realign Voyager 1's trajectory. However, something strange happened shortly after the upgrade, a discovery that left scientists around the world both fascinated and alarmed. What groundbreaking revelation did NASA uncover in Voyager's previously stored data? Could this be evidence of extraterrestrial life? Let's uncover what happened after Voyager 1 received its software update, over 15 billion miles from Earth. Imagine the most distant human-made spacecraft experiencing a malfunction with no existing guidelines for fixing it. That was the challenge NASA faced, prompting them to develop a brilliant solution. NASA issued a call for programmers with expertise in Fortran and assembly languages, programming languages from the 1940s and 1950s that most recent graduates don't know. NASA formed a specialized team of scientists to oversee a complete overhaul of Voyager 1 systems from 15 billion miles away. Over the next several weeks, the team conducted extensive research and rewrote code, taking into account the unique modifications made to Voyager 1 since its 1970s launch. After completing the update, they made a startling discovery, a forgotten set of data that the probe had not transmitted in years. Following the update, something strange happened, raising questions about how such an anomaly could even occur. To understand the context, we need to go back to the 1960s when an ambitious project emerged. A daring mission to explore multiple planets in the far reaches of our solar system. Named the Grand Tour, this plan aimed to send probes to investigate Jupiter, Saturn, Uranus, Neptune, and even Pluto. What made this mission unique was a rare alignment of these planets, an astronomical event that would occur in the late 1970s and wouldn't repeat for 176 years. This alignment allowed for a gravity-assist slingshot to propel the spacecraft on an extended path to the outer solar system. In 1977, NASA launched two Voyager spacecraft, Voyager 1 and Voyager 2, with a primary goal of unlocking the mysteries of Jupiter and Saturn. However, their discoveries were so groundbreaking that NASA expanded the mission parameters. With renewed purpose, Voyager 2 embarked on a historic journey to explore Uranus and Neptune, accomplishments that remain unmatched by any other spacecraft to this day. The Voyager's journey became a grand odyssey, examining 8 major planets, their fascinating moons, and the complex systems of rings and magnetic fields that these giant planets possess. In December 1977, Voyager 2 crossed the asteroid belt, followed 9 days later by Voyager 1. In February 1998, Voyager 1 achieved a historic milestone, surpassing Pioneer 10 to become the most distant human-made object in space. By 2002, Voyager 1 had left the solar system, moving beyond the ecliptic plane at an angle of 35 degrees and traveling at 39,000 miles per hour. Voyager 2 took a different path, moving below the ecliptic plane at a 48-degree angle and a speed of 3,450 miles per hour. Voyager 2 holds the record for reaching more planets than any other probe, while Voyager 1 stands as the farthest traveled spacecraft, venturing farther from Earth than any other human-made object. Both Voyagers completed their exploration of the outer planets within the first 12 years of their mission, achieving their primary objectives by 1989. With the main planetary tour complete, the mission transitioned to the Voyager interstellar mission in 1990. Today, these pioneering probes continue to journey into the unknown, beyond the boundaries of our solar system. Voyager 1 is no ordinary spacecraft. Its construction is a testament to NASA's exceptional engineering, withstanding the relentless march of time. Among its impressive features is a robust radio communication system, designed to function even beyond the solar system's edge. The probe's large 37-meter high-gain antenna serves as a critical link for sending and receiving radio waves across vast distances, bridging the gap between Voyager 1 and Earth through the Deep Space Network stations. When direct communication becomes impractical, Voyager 1 relies on its dependable digital tape recorder, DTR, which can store around 67 megabytes of data for later transmission. To put this in perspective, signals from Voyager 1 in 2023 take a staggering 22 hours to reach Earth, underscoring the vastness of space. Equipped with cameras, Voyager 1 can capture celestial wonders, immortalizing distant planets and their moons. These cameras function based on an imaging parameter table stored in the spacecraft's computer. Although Voyager 1's camera system follows preset guidelines, more modern space probes, developed from the 1990s onward, have adopted fully autonomous camera systems, marking a shift away from Voyager's setup. Voyager 1 operates under its Command Computer Subsystem, CCS, a marvel of 1970s technology that manages various functions, including command decoding, fault detection routines, antenna pointing schedules, and spacecraft sequencing routines. This upgraded version of the CCS, originally used in the 1970s Viking orbiters, is a testament to durable engineering. Before delving into what happened after Voyager 1 received the software update, it's important to understand the longevity of the Voyager missions and what has made these probes so resilient. Voyager 1 and Voyager 2 are equipped with a sophisticated suite of scientific instruments, including subsystems and sensors that contribute to their enduring mission. These remarkable tools have enabled the probes to journey into interstellar space, where they continue to explore the mysteries of the universe, representing one of humanity's greatest achievements in space exploration. In celebration of the 50th anniversary of its historic launch, NASA remains committed to maintaining a strong communication link between Earth and each Voyager spacecraft. Equipped with a pair of small thrusters, these engines, though not used for propulsion, play a critical role in reorienting the spacecraft to ensure its antenna stays aligned with Earth. These engines adjust Voyager's position with brief, precise pulses lasting just milliseconds, enabling vital communication to continue. However, recent malfunctions have drawn the attention of scientists. Notably, Voyager 1 has encountered a series of troubling issues that threaten its operation. One of the pressing concerns is the occurrence of distorted or corrupted telemetry data. As Voyager 1 traverses vast interstellar distances, it transmits essential data back to Earth, allowing scientists to track its progress. Yet, on several occasions, the transmitted data has arrived in a scrambled or unreadable form, presenting scientists with a daunting task of decoding its true meaning. This anomaly poses a significant obstacle to understanding the spacecraft's current status and the environment it encounters on its journey through interstellar space. Complicating these communication challenges are the signs of aging and degradation appearing in Voyager 1's thrusters. These essential engines, responsible for keeping the spacecraft's antenna directed toward Earth, have begun showing wear and malfunctions. As the thrusters struggle, maintaining stable communication with our planet becomes increasingly uncertain, heightening the risk of losing critical data. Without this connection, our link to Voyager 1, a pioneering messenger of exploration, could be severed. The implications of these issues extend beyond mere technical difficulties. The loss of Voyager 1 would mark the end of an era and rob us of invaluable insights into the mysteries of interstellar space. Faced with these challenges, NASA has embarked on a dedicated mission to overcome obstacles and extend Voyager 1's operational life. By employing sophisticated algorithms and innovative techniques, they analyzed the distorted telemetry data to extract meaningful information. Simultaneously, they explored alternative methods to compensate for the weakening thrusters, considering ways to use other onboard systems or devise creative workarounds to keep the spacecraft properly oriented toward Earth. A crucial realization emerged from their efforts. A software update was necessary. In 2015, NASA issued a request for a software engineer proficient in Fortran and assembly language, two programming languages popular when Voyager 1 was originally launched. Updating the spacecraft system proved challenging, as both Voyager probes still rely on their original 50-year-old computers, with only 70 kilobytes of memory. Engineers soon discovered that the thrusters used to maintain Voyager's orientation were showing signs of fatigue. Each time the engines fired, tiny particles of hydrogen fuel became lodged in the lines, gradually causing blockages in the system. Voyager had already switched to its backup thrusters, and if these were to fail, it would likely mean the end of the mission. With Voyager over 15 billion miles from Earth, clearing the fuel lines posed a monumental challenge. Nevertheless, the small team responsible for Voyager's well-being undertook an ambitious effort. They began developing a software update that would address the issue, transmitting it across the vast expanse of space. Voyager's onboard system consists of 3 primary computers, each serving specific functions. The main computer manages all major instruments, ensuring the spacecraft's overall health and temperature, while also overseeing the other 2 computers. The second computer focuses on Voyager's orientation, continually seeking predetermined reference points and activating the thrusters to keep the antenna aimed at Earth. The third computer stores and manages scientific data and images captured by Voyager's instruments. A select group of instruments continues to function on board the intrepid Voyager 1 and Voyager 2 spacecraft. Among the enduring instruments still operational on both Voyagers is the low-energy charged particle (LECP) detector. This specialized device, equipped with 3 sets of particle sensors, analyzes particles and measures their velocities by continuously monitoring cosmic radiation and particles from the Sun, planets, and interstellar space. The data gathered by this detector offers valuable insights into the composition and behavior of these cosmic elements, providing a deeper understanding of the vast mysteries beyond. Both Voyager spacecraft are also equipped with a cosmic ray instrument that detects highly energetic particles originating from the Sun and other cosmic sources. This instrument plays a crucial role in monitoring particle abundance within the Sun's protective influence as well as those from interstellar space. These measurements have been instrumental in helping scientists determine the exact moment Voyager 1 crossed into interstellar space. Another essential instrument still active on both Voyagers is the plasma wave subsystem. With 2 long antennas extending at right angles to each other, this subsystem continuously records the electric field components of plasma waves encountered during the spacecraft's journey. Originally intended for studying phenomena around the outer planets, it now plays a vital role in unraveling the secrets of plasma waves in interstellar space, providing valuable data for scientific analysis. The magnetometer, initially used to study magnetic fields around the outer planets, has also taken on a new scientific mission. It now investigates the transitional boundary between the Sun's influence and interstellar space by measuring magnetic field properties at this frontier. This instrument helps illuminate the complex interactions between cosmic forces at this boundary. Voyager 1 and Voyager 2 also rely on the plasma science instrument, which remains crucial for data collection. This instrument detects low-energy particles in plasma and can determine specific particle speeds and, to some extent, their origin direction. As the spacecraft move further into interstellar space, the insights from this instrument become increasingly invaluable. While some instruments have succumbed to time or have been deactivated to conserve power, the Voyager team has made significant efforts to keep the remaining systems functional. In 1998, non-essential instruments were permanently shut down, and heaters on both spacecraft have since been deactivated as part of power-saving strategies. The power for each Voyager is supplied by 3 radioisotope thermoelectric generators, RTGs, which convert heat from the decay of radioactive plutonium-238 into electricity. However, as the plutonium-238 continues to decay, a time will come when it can no longer meet the power demands of the instruments, ultimately ending all scientific operations. This power decline is anticipated to occur around 2025, but the Voyager team is working to extend the missions until 2027, a milestone marking 50 years since the spacecraft's initial launches.